Hello everyone, welcome to topic 2.5 Lewis diagrams. These are the notes. In this, the essential knowledge we'll come away with is that Lewis diagrams can be constructed according to an established set of principles. Moving into our notes. So Lewis structure shows a representation of how atoms connect to form a molecule. Lewis structures must account for all of the electrons in that molecule. You'll want to remember these, that a line or a pair of dots between two atoms represents a shared pair of electrons forming a single covalent bond. That two lines or four dots between two atoms represents two shared pairs, which is a double covalent bond. 3 lines or 6 dots represents 3 shared pairs, which is a triple bond. And then a pair of electrons on a single atom is a lone pair of electrons, and these are non-bonding electrons. Okay, so we're going to review how we draw these. This was technically covered in your first year chem, but we will review it. So the first thing you should do is determine the total number of valence electrons. Then you're going to draw a skeletal structure. The way I break this down is that your first part, so step 2A is to determine central atom. So the one that goes in the middle, that is the one that will form the most bonds, or is least electronegative. Now hydrogen tends to be a lower electronegativity than anything else, but hydrogen is never in the middle. And then we have 2B, which then on the central atom, you bond with other atoms. Okay, and you keep doing this until you end up with 8 on the central atom. You place remaining electrons as lone pairs so that you can fulfill as many octets as possible. And then if you run out of electrons before you have satisfied every atom's octet, you form double or triple bonds. So the best way to get familiar with this is to practice. So the step 1 is to determine the total number of valence electrons. So we're going to do that with methanol here. So we have 4 from carbon, because carbon's in group 4A or 14, so it has 4 valence electrons. And then we have 3 hydrogens, so each hydrogen atom has 1 valence electron, plus 6 oxygen, plus 1 more hydrogen. Notice I just went in order of how the chemical formula was written. So I sum those together and I end up with 14. So now I can go to step 2, and my step 2A was to determine who is central, and that is carbon, because they form 4 bonds or need 4 valence electrons to have a complete octet. Then I need to form bonds with others. So we have more than 4 atoms, so I'm going to assume that carbon will form all of its bonds. And we have 3 hydrogens that are right next to the carbon. So these 3 hydrogens say it's right here. And then we have to figure out who goes on this next arm. Well, you can either say hydrogen, but if we put hydrogen here and then an oxygen here, hydrogen only forms 1 bond. So we can't do that. So we put the next one in, which would be oxygen, because it forms more bonds than hydrogen, needing 2 valence electrons to get to an octet. Okay, so then we count our electrons used, and we use 10. 2, 4, 6, 8, 10. And we have 4 left. So in step 3, and now you don't have to rewrite this after we go through these notes, but it's here so that way we understand. Step 3 is place remaining electrons on as lone pairs. So carbon is fulfilled in its octet, and each of the hydrogens is full. So we'll place 2, 4 on oxygen and count, and it does have an octet. Then step 4 says to form double bonds. This is not applicable here because everything has an octet. So moving on to formaldehyde, or CH2O. Again, step 1, determine total valence electrons. And you end up with 12. Step 2 is to draw your outline. So carbon again is in the central because it forms the most bonds. Then you, I would say, invite your guests in because it's kind of like a party. So hydrogen on each side and oxygen at the top. It actually doesn't matter where you put them, just as long as they are each on there in a separate bond around carbon. I like to make it symmetrical because it makes me happy, and we see that chemistry tends to favor symmetry. So we use 6, so we have 6 left. So I say feed your guests first. So if carbon is hosting the party, we're going to give all the food first to oxygen, and then carbon will get leftovers. So oxygen we added 2, 4, 6. We've run out. We can't add more. So then we look at this and we see, oh, carbon's not fulfilled, so it's going to share a pair with carbon. Oxygen will share a pair with carbon. And so that gives us, and it doesn't matter where those 2 lone pairs are on oxygen as long as they're shown in pairs and on oxygen. But that double bond comes in and it completes the octet for carbon, and then oxygen's octet is still fulfilled. Okay, so let's look at some practice. So we're going to draw the Lewis diagram for this. Now we're going to assume that this is chlorine. Okay, very seldom will you ever be given iodine, but if we look at how everything is bonding, we will see that there aren't enough electrons for iodine and carbon to be bonded in this way. So you need to always pay attention to your octet because it will tell you if you're assuming the right elements. Okay, so then first step is to determine valence electrons. So 2 carbons plus 3 hydrogens plus 1 chlorine. This gives us a total of 18. So step 2 is to draw our outline structure, and carbon is going to be in the center, but we have 2, so they're going to co-host. So we use 2 there. So we have 16 left. And now we're going to bond to the others. So 1, 2, 3, 4, keep it symmetrical, and we have 3 hydrogens and 1 chlorine. Now, does it matter where you put the chlorine and where you put the hydrogens? No. Just that each carbon is bonding to 2 other atoms besides the other carbon, and that hydrogen is not central. Sorry, guys. So then we will, step 3, I'm just going to add it here because this is getting silly. Step 3 is to feed your guests. So we use 2, 4, 6, 8 more. And so we are left with 8. So I'm going to do 2, 4, 6, 8. Okay, so chlorine's octet is full, carbon on the right's octet is full, but the carbon on the left is not. So step 4 tells me to move this pair in and form a double bond. And I'm left with that. And we check 2, 4, 6, 8, 2, 4, 6, 8, and 8 around chlorine. All of the ones that need an octet are filled, and hydrogen only bonds once. Okay, so now please pause the video and attempt question, or the we do, for these. Okay, as a hint, if we see a charge on something, you need to put the drawing in brackets and put the charge in the top right to indicate that there's a -1 charge on that entire thing. So please pause the video and attempt these yourself. Okay, so for this, we see that we needed to add an electron here because of the on hydroxide because of the negative charge. That on the BCl3, we are doing a reduced octet because boron does not have enough valence electrons to do a complete octet, so it just pairs the 3 electrons that it already has with another electron from each of the chlorines. Then sulfur, because it is in the 3 shell, like third period, it has access to the 3d orbitals, so it can do an expanded octet, and because it's bigger, it will. So we know fluorine doesn't like to bond more than once because it's highly electronegative, and it only has 1 unpaired electron, but sulfur has 6 electrons available technically for bonding, so it does an expanded octet. So this covers a few exception rules in these practice problems. Okay? Another one to pay attention for that would do an exception rule is phosphorus. Thank you guys, and check your work after you do your UDOs.